So this is part 2 of this physical stressor lecture on noise. Very similar learning objective to the first lecture. It's the potential environmental and occupational health impacts of noise exposure. Well, why do we care about noise? It's the most common occupational hazard. At least 30 million workers are exposed to hazardous noise levels, and it's the most common occupational disease. And most importantly, it's preventable. There's lots of different ways to prevent this, and there are lots of different exposures, as you can see here in this photo. Well, just a quick review of sort of the physiology around hearing. I think we're all familiar with the outer ear. Now, what's important in the functioning of this system is that the middle and inner ear are where the action takes place. It enters the ear, sound pressure itself enters the ear as a vibration that's funneled through the tympanic membrane and vibrates the ossicles in the middle ear, which vibrate the fluid in the cochlea. Now the fluid pushes against the hair cells, which then transmit a signal to the central auditory system within the brain. I mean, that's how sound pressure gets turned into what we're familiar with as sound. Well, noise is a pressure wave. You'll often hear noise referred to as sound pressure. Now that wave has a particular amplitude related to the intensity of the noise. All noise travels at the same speed at normal temperature and pressure on this planet, which is 767 miles per hour. Now that's a finite speed. It's less than the speed of light, but as a consequence of traveling relatively slowly, you get interesting effects like the Doppler effect that we're all familiar with when you're standing near a train as it goes by. It seems to get very loud very quickly and then declines very rapidly as it goes past. But think about the wavelength and the frequency issues as the velocity is related to both the frequency and the wavelength. So intensity are essentially changes in atmospheric pressure that can be directly measured as newtons per square meter, and this is sound pressure. Now the range of human hearing is over this scale you can see here. It's around 2 to the 10 to the minus 5 newtons per square meter to about 20. That gets translated in what we call decibels, which is on a log scale. Usually the range of human hearing is on the order of 120 is the high end, from 0 being the low end. 140 decibels is really the pain threshold. Since this is on a log scale, note that you go from 2 times 10 to the minus 5 to 20. We use this handy decibel scale. Now here's an equation here. I don't think it's all that important. It's just for you completists, how you convert sound pressure levels to decibels. So the range of human hearing is somewhere between 20 and 20,000 hertz or 20 kilohertz, and young people as we age, our hearing degrades. So what you have here in this graphic is on the y-axis there's the sound pressure level in decibels, and on the x-axis is frequency. And then you can note in the middle here it shows you conversational speech. That's sort of the range of human hearing. So we're most sensitive, our hearing is most sensitive in the range of about 1,000 to 4,000 hertz. And remember, those are cycles per second. And most of us our speech is between 300 and 4,000 hertz, depending on how, sort of the amplitude and the intensity of our speech. Now note, around this in that sort of conversational speech range, you can see some things that are around it. For example, one example is a lawnmower. Those are between 80 and 100, but the sort of sound they make is between 1,000 and 10,000 hertz. And things that hurt, like rock concert loud or gunshot loud, or you can see up around the very high end of the decibel scale. Now, there's a couple different ways that noise gets weighted. This is sort of a technical fine point. that I don't think you need to worry a lot about. The typical scale we use is called A weighting, and it corresponds to what's called 40 Fawn equivalent loudness contour that's shown here. Now the A weighting scale is the most commonly used, and it most effectively represents how we perceive sound. Now all noise measurements are performed typically with using the A weighting scale. C weighting is sometimes helpful to determine the frequency characteristics of a noise because it's a little better at doing that. But the C scale is better also at low frequency noise. And when we were measuring, if you think back to the natural resource lecture, I talked a little bit about the noise around these oil and gas sites. The C-weighted noise we tell people is the noise you can feel, as opposed to A, which is the noise you can hear, because it's strongest in the typical range of human speech. So how do we measure hearing? It's typically measured with what's called an audiogram, and it measures the softest sounds you can hear for various frequencies and decibel levels. And sort of the diagnosis of noise-induced hearing loss, they have required test frequencies, and they're between 500 and 6,000 hertz. And then you would typically test each ear separately. And you can see an example on the computer in the picture here where they've got the results graphed for each ear. Now, there's a couple different kinds of hearing loss. There's what's called conductive hearing loss, which is loss across all frequencies, and it can result from middle or outer ear abnormalities or scouring of the eardrum. Now, what's called sensorial neural hearing loss is actually damage to the hair cells in the organ of Corti, and you can see in this is a more detailed version of the physiology of the ear graphic I showed you earlier in the lecture. You can see where the organ of Corti is. But this can be noise induced, or it can be due to aging, or a combination of both those things. So hair cell damage, it happens when you have excessive noise, and the hair cells go from looking like these healthy ones here to the damaged ones on the right. Now, noise-induced hearing loss, what happens is that our threshold of hearing declines, and typically there's this notch configuration, which is typically seen at 3, 4, or 6,000 hertz. So you can see here, this particular individual had noise-induced hearing loss around 4,000 hertz, where it was most acute, and little recovery at some of the higher frequencies. So the risk of hearing loss is basically two types. NIHL, noise-induced hearing loss, can result from two types of exposures, either long-term exposure to a loud noise source, typically sort of occupational noise sources, or a single very loud event. In the end, risk of hearing loss is related to the dose that you get. Now, the frequency around 4,000 hertz is the most damaging, because that's the most sensitive hearing frequency for most humans, so therefore it's the highest risk. But it's not just frequency, it's duration of exposure. Longer is worse, but recovery time is also important. Now there's also sort of individual factors in humans' adaptability and physiology, but in the end, it's noise-induced hearing loss is the major cause. Are these two examples shown here. So OSHA, the Occupational Safety and Health Administration, has developed a noise standard with these two sort of actionable thresholds. One is once you get above 85 decibels on the A-weighted scale as an 8-hour average, it's an action level triggering employees having to have annual audiograms. Now above 90, it's an 8-hour as an 8-hour average. It requires engineering controls that are things that will reduce the noise levels, and think back to the hierarchy of controls that we talked about earlier in the course, and or hearing protection. Now look at the table on the right. Notice how the hours and the sound level vary together. So you can be exposed to 85 up to 16 hours, but 115 for only a quarter hour, and never above 140 decibels on the A-weighted scale. So OSHA has also developed programs, for example, hearing conservation that involve performing noise monitoring, developing engineering and or administrative controls first, and then above 85, you have to have a hearing conservation program. That includes these annual audiograms I mentioned earlier, noise monitoring, but also, most importantly, making hearing protection available. And with that, you'll need employee training. So here's a good rule of thumb for you to remember, if nothing else from this lecture, is a noise is too loud if you have to raise your voice to talk to someone who is just 3 feet away from you. We've all been in noisy environments. You'd be surprised how loud it is, for example, in a room full of people, say a restaurant or a party where a lot of people are talking. But if you're having trouble hearing somebody who's 3 feet away and you have to raise your voice, that means you're likely close to or above at least 85. So noise is too loud if your ears ring or buzz after exposure, you have pain, you can't hear high-pitched sound, and speech and other tones seem muffled after exposure. There's what's called a temporary threshold shift, i.e. you're unable to hear below a certain level because your threshold has shifted up. And as a consequence, everything seems muffled. Now, note one really important thing here is you can have hearing loss without any pain. So a lot of the damage can be, as they say, relatively painless, unfortunately. So if you're interested in sort of looking at this and hearing what this sounds like, if you've got a computer with either headphones or good speakers on it, you can go to this link and sort of play with it. But also note the different sort of devices that are and the sound level associated with each. So one of your key populations at risk for noise-induced hearing loss are construction workers. And this is an infographic you can see that was put together by the CDC and NIOSH. 73% of all construction workers are exposed to over the NIOSH recommended exposure limit. So they've put this together in a way that you can sort of visually see what that represents as well. So here's some typical noise levels with tools that are commonly used by carpenters. Here's the NIOSH recommended exposure limit of 85, and you can see normal conversations typically around 60, a whisper is 30. But then look at what hand drills, spray painters, chainsaws, hammer drills, and these a lot of these pneumatic precision drills and nail guns and things like that are really pretty loud. These are all examples of why this is a noisy profession. So in the end, the rationale for measuring noise is to assess the potential risks associated with damage and the nuisance properties and evaluate the effectiveness of various controls. Now, when I say nuisance properties, I mean what's the effect not just of the person, but nearby to people living near there or working near there. And again, it gets back to intervention, as always. So one of the tools you use to do this is what's called a sound level meter. This measures the total sound pressure level of noise, and it has options for a bunch of different weighting networks. This is a relatively expensive one. My group has recently written a paper on using cell phones to do very similar things that we published in a journal. And with the right app and an external microphone, turns out you can at least get the levels right, if not some of the important frequencies. Now, sound level meters like this can be handheld. They cost a couple $100, but they're useful for spot surveys and constant noise sources. What's known as a Type 2 sound level meter is an ASTM standard, and that's sort of the gold standard for determining how to measure and assess noise. And as you can see here, they have sort of these readouts that you can just sort of hold up, but the ones that typically come on your phone are not nearly as accurate as these, although they're generally fairly reliable. Now, if you want to get even fancier, there's a thing called an octave band analyzer that will tell you what the sound pressure level is at each frequency or octave band, and it tells you this in real time. So it's good for determining the character of the noise. Certain frequencies, as we noted earlier, have greater damage potential, and will also suggest things that you should consider controlling, or how effective the controls that you've put in are. Now, a sound level meter and an octave band analyzer are more for research-oriented noise monitoring. When you want to know exactly what someone's exposed to, you can put a dosimeter on them. This is a good example of one. What this does is it measures noise over a work shift, and it logs the results. You can set it up so it will measure and tell you whether you're exceeding some level, either the OSHA standard or the action level, at what's called here the threshold level. And typically it will do these in about 5 decibel increments. You can set it up for slow response, for A weighting, C weighting, a bunch of other weighting networks typically, but you can only measure one at a time, and they need to be calibrated both before and after use. Now the key thing with this is you want to set this microphone up near an employee's ears, so you're literally measuring what they're hearing. But this is a tool that's widely used for noise monitoring in industries, particularly in noisy industries, because periodically they've got to go on and demonstrate whether or not they have to have an official hearing conservation program. So framing this in terms of the hierarchy of controls that we've talked about as a systems thinking approach in this class, administrative controls would be things like worker rotation or enclosing particular rooms with particularly noisy processes. Engineering controls ideally should be the first option. You want to make processes as quiet as possible. But if controls aren't feasible, you have to end up using personal protective equipment like those shown here, and usually a combination of them. For example, both earplugs and earmuffs. So engineering controls, there's a bunch of examples here: enclosures, barriers, reducing the speed of rotating machinery, muffling the air exhaust, dampening vibration, or reducing the number of teeth on cutting devices are all things that reduce the amount of noise that they produce typically. Now, if you have to go to PPE, there's lots of different hearing protection options. There's plugs or muffs. Often, if you really want to have something that's effective, you use both. One needs to follow the manufacturer's instructions, and plugs must be properly inserted. Typically, it's best to sort of demonstrate these. You need to really you get those like little yellow foam earplugs. You need to really wind them up into a ball and put them in, and the proper fit must be maintained. You don't want to make homemade protection like cotton and things like that, because these things are designed with particular tolerances and can be fairly effective. Although these ones, for example, shown here in this picture on the left, bottom left, that this one here circling in red, these are not particularly effective. The ones, the earplugs with the hanging piece. Often, as I said, the combination of plugs and earmuffs are key. So here's a range of hearing protection that gets used, from, as I said, the earplugs and earmuffs. What's interesting here is for particularly onerous and noisy locations where you need really good hearing protection, these are actually custom made. If needed, they'll make custom that fit exactly. They come in and take an impression of your ear and fit these in so they provide a really good seal. This is often last resort sort of approach, but these are quite effective and work better than some of the others shown here. So how effective are these various forms of personal protection equipment? Now OSHA will certify everything. You'll note here the label that says, noise reduction rating of 25 decibels when used as directed. Now, that's what it says. In practice, remember, this is a log scale, and a good rule of thumb is you don't count on more than reduction of about 10 decibels, which is how you get this. What the first bullet notes here is sort of a rule of thumb. If the NRR is 25, you subtract 7, then divide by 2. In this case, that would be your real protection is approximately 9 decibels, but that's still healthy. And you've got to remember this is on a log scale, so that that's a big reduction. But in the end, you can't count on any sort of PPE giving you much more than 10 decibels, except if you combine them. Now, I mentioned that earmuffs and plugs often work well together if you get people to do it. So that'd be more like 15, because you can add, as this notes, about 5 decibels noise reduction when wearing the two of them together. So thinking through the hierarchy of controls and noise-induced hearing loss prevention, here it is from elimination all the way down to PPE. Now, elimination is fairly clear. What's not as clear is substitution, which is often not an option, but there are some sort of personal sound choices, as this notes, you could use a rake instead of a leaf blower, for example. Now, there are other things you can do that have impact, although they're increasingly at the personal level. Is the right arrow notes. You see increasing population impact is designing appliances or tools with lower dBA or administrative controls implemented under the 1972 Noise Control Act before you get to having to resort to PPE. So earplugs or muffs are a good option, but requires both training and getting people to buy in and education about the major impacts of noise-induced hearing loss. So in closing, I thought I'd show you one more infographic. What's really good about this one is not just the color-coded scale from green to red, but also the examples here showing you that between 80 and 90 prolonged exposure causes hearing loss. And what's interesting about this is it's stuff that you use every day often. For example, hair dryers or motorcycles or truck traffic are in the range that will damage your hearing, believe it or not, at least prolonged exposure. So you've got things, if you look left down the scale, there's a lot of surprisingly loud things in one's house, like an alarm clock or a vacuum cleaner. We still run into the things that are 100, 110, 120. Power lawnmowers, chainsaws, and snowmobiles are all relatively loud, if not painful. And note the things that are painful: jackhammers, firecrackers, gun blasts, sandblasting, or loud concerts. All those things, short-term exposure can cause permanent hearing loss. So this ends part 2 of this lecture, and we'll pivot to part 3 shortly.